Yes, a steel frame building with a 200 amp service must be grounded for safety reasons. For a 200 amp service, the grounding conductor should be a minimum of number 6 AWG solid copper wire. There are two common methods for connecting the grounding conductor to the steel frame. Firstly, direct connection, which involves welding the grounding wire directly to the steel frame using an exothermic weld or a mechanical connector. Secondly, ground clamp, where you use a ground clamp to connect the grounding wire to a clean, bare surface on the steel frame. If you are performing a direct connection, first clean the surface of the steel frame where the connection will be made. If you are using the exothermic welding method, place the grounding wire in the weld cavity of a suitable exothermic weld kit and follow the manufacturer's instructions for proper welding. If you are using the mechanical connector method, use a listed mechanical connector specifically designed for grounding steel structures and follow the manufacturer's instructions for proper installation. If you are performing a ground clamp connection, first clean the surface of the steel frame where the clamp will be placed. Then open the ground clamp and place it around the cleaned surface and tighten the bolts on the clamp securely to ensure good electrical contact. The grounding connection should be made at a location where it is easily accessible for inspection and maintenance, and it should be protected from physical damage and corrosion. The grounding connection should be made to the main grounding bus in the electrical panel. If the building has multiple steel beams or columns, they should be interconnected with grounding wire to create a continuous path to the grounding electrode system. The grounding electrode system should consist of multiple electrodes, such as ground rods or buried plates, to provide a reliable path to earth. Grounding a steel frame building is a critical safety measure. The primary purpose of grounding is to provide a low impedance path for fault currents to return to the source, typically the electrical panel or transformer. This low impedance path allows overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and energize the circuit in the event of a ground fault. Without proper grounding, fault currents can find unintended paths through the building structure, potentially causing electrical shock hazards or fire hazards. The National Electrical Code, or NEC, provides specific guidelines and requirements for grounding electrical systems in buildings. These requirements are designed to ensure the safety of people and property. When grounding a steel frame building, it is essential to adhere to the NEC requirements to meet safety standards. The size of the grounding conductor is determined by the size of the service conductors. For a 200 amp service, as mentioned earlier, a minimum of number 6 AWG copper wire is typically required. However, it is crucial to consult the NEC for the specific requirements based on the size and type of service conductors used. The grounding conductor should be installed in a manner that protects it from physical damage. It should be securely fastened to the building structure and routed in a way that minimizes the risk of it being cut, damaged, or disconnected. When using a direct connection method, such as exothermic welding or a mechanical connector, it is essential to ensure that the connection is properly made and that it provides a reliable electrical bond between the grounding conductor and the steel frame. Exothermic welding involves using a chemical reaction to create a permanent metallurgical bond between the grounding conductor and the steel. This method provides a very low resistance connection that is highly resistant to corrosion and degradation over time. Mechanical connectors, on the other hand, use mechanical pressure to create a secure connection between the grounding conductor and the steel frame. These connectors should be listed for grounding purposes and should be installed according to the manufacturer's instructions to ensure proper performance. When using a ground clamp connection, it is important to select a clamp that is specifically designed for grounding purposes. The clamp should be made of a corrosion-resistant material, such as copper or bronze, and it should be sized appropriately for the grounding conductor and the steel frame. The surface of the steel frame where the clamp is installed should be thoroughly cleaned to remove any rust, paint, or other contaminants that could interfere with the electrical connection. The clamp should be tightened securely to ensure that it provides a good electrical contact between the grounding conductor and the steel frame. The location of the grounding connection is also an important consideration. The connection should be made at a point where it is easily accessible for inspection and maintenance. It should also be protected from physical damage and corrosion. Common locations for grounding connections include the main grounding bus in the electrical panel, a steel column near the service entrance, or a grounding electrode conductor connection point. If the building has multiple steel beams or columns, they should be interconnected with grounding wire to create a continuous path to the grounding electrode system. This interconnection helps to ensure that all parts of the steel frame are effectively grounded. The grounding electrode system is the means by which the building's electrical system is connected to the earth. The grounding electrode system typically consists of multiple electrodes, such as ground rods, buried plates, or concrete-encased electrodes that are installed in the earth. The purpose of the grounding electrode system is to provide a low impedance path for fault currents to dissipate into the earth. The size, type, and number of grounding electrodes required depend on the size of the service, the soil conditions, and the requirements of the NEC. Ground rods are commonly used as grounding electrodes. They are typically made of copper or copper-clad steel and are driven into the earth to a specified depth. Buried plates are another type of grounding electrode. They are typically made of copper or steel and are buried horizontally in the earth at a specified depth. Concrete-encased electrodes, also known as UV grounds, are grounding electrodes that are encased in concrete. They are typically used in new construction and provide a very effective grounding path. In addition to the grounding electrode system, it is also important to bond all metallic components of the building's electrical system together. Bonding is the process of connecting all metallic parts of the electrical system, such as metal conduits, metal enclosures, and metal water pipes, to create a continuous electrical path. Bonding helps to ensure that all metallic parts of the electrical system are at the same electrical potential, which reduces the risk of electrical shock hazards. The NEC provides specific requirements for bonding electrical systems. These requirements are designed to ensure that all metallic parts of the electrical system are properly bonded together. When bonding electrical systems, it is important to use the proper bonding conductors and connectors. Bonding conductors should be sized according to the NEC requirements and should be made of copper or other conductive materials. Bonding connectors should be listed for bonding purposes and should be installed according to the manufacturer's instructions. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. The grounding connection should be inspected periodically for signs of corrosion, damage, or loose connections. Any damaged or corroded connection should be repaired or replaced immediately. The grounding electrode system should also be tested periodically to ensure that it provides a low impedance path to earth. Grounding is a critical aspect of electrical safety. Proper grounding helps to protect people and property from electrical shock hazards and fire hazards. When grounding a steel frame building, it is essential to adhere to the NEC requirements and to use proper grounding techniques. Safety is paramount when working with electricity. Always de-energize circuits before working on them and use appropriate personal protective equipment. If you are not comfortable working with electricity, consult a qualified electrician.